Um, Professor Lobodek couldn't be here today, so I'm giving the lecture instead of him. My name is Hossein Tabatabai. I am a PhD student in computer communication sciences, and I'm working with Professor Jean-Yves Lobodek. Well, I'm also a TA for the course, so you might have already seen me. And the topic today is external routing, or BGP. And today we'll see, when you sit in a router, how could you find your way through internet to any destination anywhere on the world. Well, the way that routing works on internet is that internet is split into some domains. Inside domains, we don't care what's the routing. It could be anything. The one that are responsible for the domain should take care of the routing, and any routing works. For example, the most widespread one is OSPF. We've already seen that through lab 4, but it could be anything else. We call them internal gateway protocols, IGP. That's old terminology. Basically, is the internal routing protocols. However, to interconnect different domains, we have to do BGP, and that's the topic today. Why do we do this? Well, why do we need inter-domain routing? Because of lots of reasons. So I give you 2 reasons here. First of all, internet is too large. So internet is very large, and if you want to do simply OSPF everywhere, that would not scale. Because if you remember how OSPF works, OSPF consists of every router advertise all these neighbors, and that is flooded throughout the network. And at the end, everyone have the same map of the network. And if you do OSPF on the internet, the tables becomes too large, and there are lots of flooding. That might still work if we split internet into some areas, but still internet is much larger than that. So by simply splitting into areas that does not scale still, we might do levels of areas, but that becomes very complicated. So we cannot do simply OSPF throughout the internet. First, because it's too large. The better reason is because internet is heterogeneous, meaning that there is no one entity that owns internet. There's no one company or provider that runs internet. Rather, internet is a collaboration of several providers or entities. Cool. Internet is self-organized, basically. So why is the problem? Well, if you think about it, how OSPF works, OSPF is a router on OSPF should run shortest path. So algorithm of shortest path, which requires to know what is the cost, what is the weight of each link. And we cannot possibly agree on some cost globally. So if you have some links in China, we cannot converge on same global cost, same global weight on a link that is in China, or the one that is in Switzerland, or the one that is in the United States. That is impossible because, as I said, there is no one entity that owns the internet. Inside domains, we hope that there is one person responsible for that has the knowledge of how this domain works, and based on some reasoning, put some weights on the links. For example, you might say this link is a backup link, is a backbone link. I don't want to have lots of traffic on it, so I put a high weight on it as a backup. However, we cannot do that on the internet. And that's why we have hierarchy of routing. So we split internet into domains. Domains, for example, is EPFO is one domain. Switch is one domain. Swisscom is one domain. Inside domain, we could do anything as long as we do the routing correctly. The most widespread one is OSPF. To interconnect such domains, we do BGP. A bit of terminology. Well, I said domain. A domain is also called autonomous systems, or AS. And AS is identified by 32 bits. Again, we have here dotted decimal representation. We have 2 blocks of 16 bits, and we represent the decimal version. For example, this is the AS number of switch. It is AS559. Switch is a provider that provides internet connectivity for Swiss universities. So EPFO is connected to internet via switch. EPFL is also a domain, is also AES, but it doesn't have a number. So it's also called Autonomous Routing Domain, AES, ARD. ARD is AES without a number. Why don't we give EPFL a number? We could, but it is because to simplify the story, EPFL is hidden behind switch. So all traffic that comes to EPFL goes out of EPFL, goes throughout switch. So it is a so-called a stop domain, and therefore it doesn't require an AES number. To simplify the BGP tables, as we see later, we do not give EPFL a number. That's a very high-level explanation of how BGP and the routing protocol inside domains interacts. Here, I'm showing 4 domains. Each cloud represents one domain, one autonomous system, one AES, A, B, C, and D. Well, as you can see, inside domains, I could run whatever I like. For example, in this domain, I'm running OSPF with areas. In this one, I'm running RIP, and everyone is different. However, to interconnect such domains, to do the inter-domain routing, we must use BGP, and the latest version is version 4. Doesn't relate to IPv4, that's the latest version of BGP. Couple of differences. We will discover differences of BGP and OSPF a lot during this lecture, but one of them we could see here. A boundary router in OSPF, when we have different areas, a boundary router, for example, this one, is in the intersection of 2 areas. So it is present in both of the areas. For example, D4 is also in area 0 as well as area 1. This is not the case in BGP. In fact, in BGP, boundary routers are into different domains. However, they are connected. For example, here, we have one router that is in area D and another router that is in area A, and they are connected. This is because domains are independent things. You might have one domain that is in North of America and another one that is in Europe. So they cannot have intersection. What is the goal of BGP? The goal of BGP is, as I said, if you sit on a router and you want to find a path through a destination, that can be anywhere on the world, you want to have a route there. You want to have a path there. And that's what BGP does. And the method of routing of BGP is very different from OSPF and is based on 2 new routing, which is called path vector routing and policy routing. I will explain path vector routing on this example. Well, here again, I'm showing 5 different ASs. So each cloud again is an AS, no A, B, C, D, E. For example, ASA contains 2 network prefixes, N1 and N2. So what an AS does is through BGP, it will announce its neighbors, it will announce to its BGP peers that I am A and I have network prefixes N1 and N2. If the policy in B agrees, we will see what I mean, but as we assume here that agrees, B will receive this information, accumulate the path, and send it to its other peers. What does that mean? Well, B receives this path, it will append itself to this path, the path becomes B, A, N1, and N2, and it will send it to E. What else B sends to E? Well, B also has a network prefix itself, it's N5, it will send the path to E. The other things happens in the other direction. Well, A sends this path to C. C will accumulate the path, append itself to the path. Path becomes C, A, N1, and N2. Same thing at D, D, C, A, and N1 and N2. Then if you focus on E, we will see that if you sit on E and we want to send some packets to N1 or N2, now we have 2 paths. One path that goes through ASB and reaches A and then N1 and N2, and another that goes to DCA. So now we know everything. If we look at what E knows set of all possible paths and also knows the complete path. Now we could make decision based on whatever criteria that we want. So E is now very flexible to choose what is the path that I choose to send some traffic to N1 or N2. And it can be anything. For example, E might choose to send traffic through a path that is shorter in the number of ASs. For example, the top path goes through only one AS, B. The other one goes through two ASs. So presumably, a path that is shorter in the number of ASs is more reliable. You might have a better quality. But it can be anything. I mean, that's where policy routing kicks in. For example, E might not like B because B is Swisscom, E is Sunrise. So I don't want to send my traffic to, for example, Swisscom. Or it can be anything else. For example, you might think that B might copy your traffic, or you don't want to send it to B. Or B is a country that might drop your traffic, right? That is also a possibility. Or the other way around, you might like, for example, B because you have a contract with B that P guarantees to give you a good quality of service. In fact, you prefer to send your traffic to someone that gives you a good quality of service. That's where policy routing comes in. But with BGP, this is a very high-level overview of BGP. With BGP, every domain could find a set of all possible acceptable routes to a destination. Based on policies, based on some criteria, it might choose the best one. But as I said, it's an overview of high-level overview of BGP, which is fairly easy to understand. However, BGP runs on routers. So the better way to implement BGP possibly is to do the routing inside the domains and run BGP at a higher level, at the server level, for example, a software-defined networking level, where you control what happens between areas. But that's not the way that it's done. So BGP, in fact, runs on the same level of other routing protocols, such as OSPF, on routers. So there are lots of overlaps. Sometimes there are lots of conflicts, and there are lots of collaboration. And that makes it a bit complicated, and we will discover such sorts of complication on BGP. One of them we will discover on this example. So here is an example that we have, again, 5 domains, and the focus is domain D3. In D3, I have 5 routers, so each box is a router, C, D, R, E, F. The dashed lines, the dotted lines, if you like, are a physical connection. So for example, there's an Ethernet cable that connects C to E. These routers are boundary routers, the ones that are at the boundary, they are boundary routers because they have an interface to an external domain. So they must speak BGP. Well, that's a goal that I see here. Well, here our domains with some mysterious way exchange some information, but that exchange of information is done on the boundary routers. For example, here. What about R? Well, in this example, I assume we do not run BGP on R because it's not a boundary router. We will see today in some examples we have to. But for the time being, we do not run BGP on R. Well, these routers must speak BGP externally, but they should also speak BGP internally. Why? Because of 2 reasons. First, if you learn a path externally, for example, if C learns a path from A, that there is a prefix that I know a path here, I should spread it internally. Well, every other router internally should know about this path. The second reason, which is important, is to have a global connectivity. So if you learn a path here, if this router C learns a path about N1, it should notify E so that E could also notify other domains. So we want to spread this information globally. So to spread such information, we use internally, we use again BGP. Or the same protocol. We could have used something else, but BGP is used again, which is a good news because we don't have to learn 2 protocols. There are a slightly different. Well, the BGP that is used to exchange information externally from one domain to another is a slightly differ from the one that is used internally. That's why the one is called IBGP, internal BGP, and one is called eBGP, external BGP. And I will explain the difference now. The way that BGP routers speaks is by establishing TCP connections. So when router C becomes alive, it must know what are other BGP peers, what are other BGP routers on this area. That we could do manually. We could write a config file in C and letting it know that you have 3 other BGP speakers in this area, E, F, and D. And whenever C becomes alive, it will establish a TCP connection to each of these peers. As you could see, these peers are not necessarily unlinked. For example, F is not directly unlinked to C. However, there is a path, so we could establish a TCP connection. How could C establish a TCP connection with someone that is not unlinked? Oh, that's not a problem, because inside domain, we run another routing protocol, another IGP, for example, OSPF, and therefore C knows a path to F. Then every BGP speakers establish a TCP connection to everyone. This is what we call BGP mesh. So inside the domain, we have a full mesh. Now, every BGP speaker sends information directly to every other router that is different from OSPF. In OSPF, you flood the information to all of your neighbors. All your neighbors receive this information. They again flood it. That's how information is repeated inside a domain. In BGP, the way that is done, every router is peer to other routers, to other BGP routers, and send the information, send BGP updates directly to them. Therefore, the first difference of IBGP over eBGP is the route that we learn internally should not be repeated internally. Meaning that, well, if C learns a route from, for example, A, it will directly send this new route to D, F, and E. And it should not be repeated by others, because if D repeats the same route to E, that's second-hand information. E already received that route directly from C firsthand. That's the first difference of IBGP over eBGP. The other difference is that, well, over IBGP, we do not append our AS number. What does it mean? Well, as we say, when we go from one domain to another, BGP calculates the accumulated path. So we append the new AS number to the path. For example, when we go from A to B to E, B appends its own AS number to the path. However, internally, we should not do that. Oh, that's also obvious. There is another difference. The next hop is not modified. I will explain it later. Time for a small quiz. So the speak up room key is this one. Correct, it's this one. And I was wondering if you could join the speak up. So I opened the first poll. The first question is that I'm giving you 2 statements, and I'm asking which one is true. First one is saying that 2 BGP peers must be connected by a TCP connection. The second one is saying that 2 BGP peers must be unlinked. I'm asking which one is always true. So I close the poll in a second. Okay. Well, the majority says A, meaning that 1 is correct, which is the correct answer. So I already give you an example. I already reveal the answer. For example, C and F are peers, or BGP peers, but they're not on link. And it's not, shouldn't be the case. Well, because we do TCP connection. It could be your peer, could be anywhere inside the domain. That's one difference with OSPF. With OSPF, your neighbors, basically the one that you talk with, are exactly on link. So exactly your on-link neighbor. Let's go through a more sophisticated example question. Well, here is the same setting that we discussed, and here I'm proposing 3 possible BGP updates, 3 possible BGP announcements. What's the syntax? So the first one is an announcement that C sends to A. What's the announcement? Well, it's a path to network prefix N1, which goes through D3, D2, some X, and N1. The second one is announcement that D sends to E. He'll say to E that, well, there is a path to N1 that goes through D2 and X. And the third one is the same announcement, but this time C sends that to E. And I'm asking which of these might be a possible BGP updates. So I'm opening the poll. So I'll close the poll in a couple of seconds. So the majority says it's D. 1 and 2 are valid or valid announcement, which is a correct answer. So let me explain it on this figure here. Well, what's 1? Well, 1, C is informing another router in another domain, a route that is this area has learned externally. Possibly was learned from D. So D has learned that there is a route to N1. It goes through D2, and over IBGP was sent to C, and C is now announcing it to other domains. That's exactly what we have seen in this here. Well, here we haven't seen who is sending such notification, but that's the announcement that external announcement that we do. That's a primary role of BGP to have global connectivity. What about the second one? Well, second one, D has learned this route over eBGP and is now announcing it internally over IBGP. So D is peer with E and is sending it over a TCP connection. Well, there is a route that I have found. We could see the difference between eBGP and IBGP. But first of all, internally, we do not append ourselves. So D did not append D3 to the path. And the second difference is here. Well, this one is wrong because that's the same information, but the second-hand information, C has repeated something that has learned internally. C has learned this route through D, and it is repeating it eternally. There is no use for that because BGP with BGP inside a domain, every BGP speaker is directly paired with other BGP speakers. Therefore, everyone receives information firsthand. And therefore, C do not have to repeat the information. Cool. What we have seen is that because of path vector routing, a router will receive set of all possible routes to a destination. Now, since you have all set of routes and have a complete route, it's very flexible. So it could, based on some rules, based on some likes and dislikes, it could pick the best route, or it could reject some of the routes. And that is done over policy routing. To understand that, we should understand that there are mainly two types of relations between people on internet. Well, one is customer-provider. For example, EPFO is a customer of Switch. So as I said, Switch is a provider that provides internet connectivity to Swiss universities as well as EPFO. Well, EPFO pays to Switch to be connected to all around the world. So we have customers that pay to some provider to have connectivity, and we have providers that receive revenue because of their customers. Another type of relation is shared cost peer. So we have several providers that should collaborate with each other to provide service to their customers. For example, if you are at home and you are connected to Swisscom, you want to be able to connect to a server at EPFO, and that's because Switch and Swisscom collaborate with each other. Normally what they do, for example, if you have two equal size provider, two equal weight provider, they might decide to not pay each other anything and only divide the cost that they use, for example, for a link that is between them. Most of the time, you have a provider that is much smaller other than another provider. For example, Switch might be connected to another provider that is a worldwide provider, such as AT&T. Then Switch becomes a customer of AT&T because Switch provides connectivity to 20 universities and AT&T provides connectivity to anywhere in the world. So Switch must AT&T something. What are these agreements? Well, these are private business agreements. They are not dictated by BGP or IETF. They are dictated by no one. So if you're in business, so you could have a better business agreement with someone. They are private, most of the time hidden. We do not understand. Here is one of the examples that we could see one of the goals of policy routing. Here I'm showing three internet service providers. ISP stands for Internet Service Provider. ISP1 is a worldwide one. It has branches everywhere. ISP2 and ISP3, however, are local ones. So ISP2 is a local service provider in Europe, and ISP3 is a local service provider in North of America. Each of these service providers has their customers. So ISP1 has a customer C1, ISP2 has customer C2, and ISP3 has customer C3. These internet providers should collaborate with each other to serve their customers. ISP2 and ISP3 are connected to ISP1 because that makes sense. It's a worldwide one, and your local ones make sense to be connected to a worldwide internet provider. However, they're also connected to each other via a link. And ISP2 and ISP3 should share the cost of this link. Normally, you do not buy a link. You lease a part of a bandwidth of a link, and the more traffic you want to send, you should lease a more bandwidth, meaning that you should pay more. So it might be advantages for ISP2 and ISP3, financially advantages, to divert their traffic to ISP1. So instead of sending the traffic here in this link, over this link and pay, it might be cheaper to ask ISP1 to carry this traffic for them. For example, if a customer C1 wants to send some traffic to C2, ISP3, it might be cheaper for ISP3 to send this traffic through ISP1 rather than using this link and paying more, right? However, if you think about it, ISP1 does not want such thing happens. It's not beneficial for ISP1 because resources inside ISP1 is being used to serve some customers that is for other customers of other service provider. If C3 sends some traffic through ISP1, customers of ISP1 do not advantages anything. They just, ISP1 is doing works for others. So ISP1 would like to refuse such things and prevent such things from happening, and that's we could obtain from policy routing. A common rule that we will have with BGP is that routes that are coming from peers and providers are not propagated to peers nor providers. What does that mean? Well, It means that if C2 has a customer with prefix N2, it will announce it to its provider. It will announce it to ISP1, for example. So ISP1 receives that there is a path through ISP2, C2, and N2. ISP1 will announce this to its customer, because if a customer of ISP1 wants to send some traffic to N2 or vice versa, ISP1 is responsible for that. So it will announce it to its customer. However, it will not announce it to another provider, to another peers, because this is a route that ISP1 has learned from another peer, and this rule prevents that. And thanks to this rule, there is no way, at least through BGP, there is no way for ISP3 to figure out that there is a route to this network prefix here that goes through ISP1. Therefore, ISP3 does not know that there is a route and cannot send such traffic through ISP1. How such policies is implemented, we will see in a second. That's because of we have some import and export rules and some decision process. But before going there, let me ask you a question. Well, imagine the same example. However, I have removed this link. So ISP2 and ISP3 are not directly connected. And I'm asking you, and another thing is that we assume that every provider apply the rules that we have seen. Routes coming from peers and providers are not propagated to peers nor providers. Now I'm asking you, what is a valid path from C2 to C3? So I'm opening the poll. In fact, there is only one route, so I'm asking whether it is valid or not. So I'm closing the poll in a second. So almost everyone says that there is none, which is the correct answer. So if you apply this rule, ISP1 will not announce to ISP3 that there is the path to C2, and therefore network is partitioned. Right. That's a consequence of applying such rules. And to avoid that might happen in the internet. So to avoid that, there is a solution. Truly, at the backbone of the internet, we have some big providers that are worldwide. We call them tier 1 providers. They are connected everywhere, and they must peer with each other. And if you are a provider, you must be connected to one of them. So you have your connectivity through one of the tier 1 provider. Well, until now, we have seen what does BGP do, and now we will dive in and see how BGP works exactly. So the version of BGP that we are talking is BGP version 4, and this is a link to RFC. So we have seen that BGP routers talk to each other over TCP connections. So they become peers. They establish a TCP connection with every peer directly. And that's a good thing, because if you think about it with OSPF, you flood this information, and that was flooded by others, and one router might receive the same information through different routes. Then you should somehow figure out which one is the latest information, which one you should keep, and that was because of the sequence number. So if each message has a sequence number to let you know that it comes after or before some other messages. Since here with BGP, we are using TCP connection, we don't care about that, because TCP provides a reliable as well as in-sequence delivery. Therefore, the latest announcement that you have received from your peer is the latest announcement. So we have different kinds of BGP messages. So we have opening, the synchronization phase. So when two BGP peers becomes alive, they do some synchronization. We have a keep alive mechanism. So each BGP router periodically sends a keep alive message to his peers to let them know that there is available. If a BGP speaker does not receive a keep alive message for a while from one of his peers, that assumes that this guy is dead. The fact that the TCP connection is open doesn't mean that the other is alive. Because in softwares, you have something that hangs, but the connection is still open. But the important thing, the main principle of BGP messages is that in BGP, we only transmit the modification, which is very different from OSPF. In OSPF, you tells everyone everything, or every router says that, well, we have link state advertisement, which is basically a summary of all of my neighbors, and you will send that periodically. With BGP, we try to minimize the number of messages that the BGP peers to send each other. And the way that it is done is by only sending addition and withdrawals. Addition meaning that if a BGP router discovers some new network prefixes, discovers some new routes, it will announce it. Or if throughout keep alive mechanism, for example, it will figure out that a router is dead, a peer is dead, it will announce a withdrawal, which is good, which improves the performance in average, but not in the worst case. What is the worst case? A while ago, all BGP routers of Facebook were down. And if you reboot all of them, everyone should send everything to each other. So in the worst case, we do not do better. However, in average, indeed, we do better. Well, that's the decision process, so I will explain it with this figure here. So the heart of a BGP router is to decide based on set of routes that we have received and based on some criteria and rules, which one is the best route. And here is a mental model of how a BGP router do such things. This is not necessarily how your software is structured. You could structure your software in different ways. However, here we have all the processes and all the data structures needed to do such things. So here I assume that I have a BGP router and it has capital N peers. So it is connected over some TCP connection with to another N routers. Well, it will receive some BGP message from each of its routers. So there are a set of routes, basically. Then it will store routes that are received from its peers to a data structure called a RIB-in, which is route information base at the input. Or this RIB-in is storing from each peer, what are the routes that we have received. It's even more than that. Well, in a route that we receive from our routers, we apply an import filter, which we kick out the routes that we do not like based on our policies that I will talk about. Well, we only keep the routes that are acceptable based on the decision of this router, right? We might do some attribute manipulation. We will see routes might have some attributes. I will talk about it in a second. And this router might change them. At the end, in the ribbon file, this router has set of all acceptable routes. We might have a local rib, which is nothing different from the ribbon file. So the ribbon file basically is set of all routes to different destinations that is acceptable for this router and was learned from its peers. And also locally, because a BGP router at the end of the day is still a router that is in domain, so it will learn some routes locally, and they are also here. So we will talk about it also later today. Then out of this set of acceptable route, we should do a BGP decision process, which is for each destination, we should pick the best route, one and best route. And what are the possible cases? Well, for one destination, we might have none. So instead of all acceptable routes, there is no route. Well, we cannot do anything. We have no route to that. For one destination, we might have only one. So that becomes automatically the best one. The case that very frequently occurs on internet is that per destination, we have many routes. because internet is large and moreover extremely meshed, and therefore between a source and destination there are lots of paths. So this router for a destination has several routes, and now it must decide based on some criteria which one is the best. We will see how it do the decision. After that, it will write them on a FIP, which is a routing table, is a forwarding information base. Then this router should advertise, should announce to its peers of its decision. So this router only advertise what is the best route that I have decided, what is the best route that I have decided per destination. Again, it might do an export filter, which you might decide not to send everything to everyone because there are rules. Some of them I told you. For example, we have a rule that routes that you have learned from providers or peers are not propagated to other providers or peers. So based on some export rule, you might decide not to send them to some of your peers. Also, some routes that you have learned internally, you will not repeat it internally. So that's this export filter takes care of. Also, we might change some attribute. And moreover, these all are stored in another data structure, which is RIP out, routing information base at the output. Why should we memorize that? Because remember, BGP updates are only the modifications. So you should remember what you have already said to your peers. If some modifications occurs, if you want to send the withdrawals, you should remember what you have already told your peers and which peers you have told this, so that you could send the corresponding updates. Another important concept is that this router only advertises the best route. It does not advertise all acceptable routes. This is because if we advertise all acceptable routes, we have an exponential growth. So eventually it will fail. So to avoid such exponential growth, exponential in the number of paths, each router only advertises the best route. But it also stores a set of all acceptable routes. So we will not delete them. This is because if we receive an update that one route is not yet, no longer available, this router should replace it by another route from the set of all acceptable routes. Well, that's a mental model. What is this decision process? Well, decision process is explained here. Well, as I said, for a destination, you have set of all possible paths, and you will compare these paths based on some criteria until only one remains. And we are very flexible about that. Every router could implement the policies that it likes. It could be anything. However, we have a default setting. That's a one common sequence of criteria that router goes through. What are these criteria? Well, these are attributes. One we already seen. One is shortest AS path, meaning that if you have several paths to one destination, you might prefer the one that is shorter in the number of ASs, the one that goes through a smaller number of ASs, because presumably this might be more reliable. There are other criteria. What are these? Well, you might label some of your path. You might have priority fill for some of your path. For example, we will talk about them in detail later, but for example, what are they? Well, wait, what is it? Well, you have, you're connected to different providers, but you have a contract, you have a business agreement with one provider, where this provider, for example, Swisscom, agrees to provide a very good quality of service for you. After that, it makes sense for you to send your traffic through Swisscom, through this provider. Therefore, you label paths, you label routes that are coming from Swisscom with a higher priority. You might not label anything. These attributes might be empty. For example, if these attributes are empty or we have equality, we go down and down. Another thing that is interesting is this one, number 4. We prefer the routes that we have learned externally through eBGP over a route that we have learned internally through iBGP. This is because the thing that we have learned through eBGP is more fresh, comes from outside, Rather, the one that we have learned from IBGP comes from inside, is a second-hand information. The next one that is interesting and important is we might prefer a path that has the shortest path to next hop according to, for example, OSPF. So we haven't talked about the next hop. Well, now is the time to talk about it. Well, we will talk about it after the break. Well, see you in 15 minutes. So so I do a small recap here. So here I have said that from each peer, we will receive some advertisements, some routes, and we will apply the import filter if some of your rules to kick out some of the routes that are incoming routes. So you might not accept some routes from some of your peers. Then we have set of all acceptable routes. These are the routes that have already passed your import filter. So you could pick each of them. Then we go through a decision process where, based on some criteria, we pick the best one. We should remember that all of them are acceptable. And this decision process is explained here. Then we apply this to the routes that are acceptable for this router, and we pick the best one. So we say that there are lots of criteria, and we're very flexible. We could do anything, and this is what we call a default setting or default rule, a common sequence that you might find in default router. So there are different criteria. You start from the top. You compare routes against each other until one of them is the main. And the one that we have reached was the shortest path to the next hub. And I'm going to explain what next hub is. So we'll use this example. When, for example, D learns a path that is in D, so D learns a path from B, the next hop for this path is the interface of B here. That's the exiting interface of this network. Basically, that's the interface that you could reach the guy that advertises this path. Right. One important thing is that the way that people does this is that at the boundary, we assume that we know the IP addresses in each of the domain. Meaning that if we sit at D3, D3 must know the IP addresses at the boundary at this interface of B and this interface of D. Same thing here. They are known internally. And therefore, if you run OSPF, for example, in D3, all routers know the path to the next hop of the routes, which are the exiting interface here. And another difference of IBGP over eBGP is that something that is repeated internally over IBGP, the next hop is not changed. The next hop always remains the entering interface of another domain. For example, if D learns a path from B, the next hop is here. Then B will advertise this route over IBGP. And in these routes that, for example, E received this advertisement, the next hop is still here. I will talk about it in details in the next example. And one of the criteria that we care about is the shortest path to next hop, because the next hop, as I said, we treat it as an internal IP address. So if you run OSPF, you know what is the cost of the different paths to reach this next hop. It would be clearer in the next example. If we could not break the event, so we compared everything. We have still some routes, acceptable routes. We pick one at random, basically. We pick the lowest BGP identifier. Here is one fundamental example. It's a very important example. Simple but important. Well, we assume that we have two autonomous systems, ASX and ASY. In each, I have two routers. In ASX, I have R1 and R2. In ASY, I have R3 and R4. Plain lines here shows a physical connection. meaning that R1 is directly attached to R2, R1 is directly attached to R3, and same here, R2 is directly attached to R4, and this is a TCP connection. Well, R3 and R4 are not necessarily on link, but there is a path to it. So it's obvious that every router that I'm showing here must speak BGP because all of them are by routers and they should talk eBGP to talk to the outside and iBGP to talk inside. Another thing that I'm showing here, I'm showing the IP addresses of the interfaces at the boundary. For example, the north interface of R3 has an address 1112, and the other one is 1111. So as I said, at the boundary IP addresses are known to each of the ASS. Therefore, when you connect two domains, they should agree on several things, and one of them is what IP address scheme, what IP addresses we should allocate to these interfaces, because that should not contradict the IP address scheme inside each of the domain. For example, R4, this address 111 is visible to R4. Is in, for example, if we do OSPF, we could find in the routing table of R4 a route to this 1111 here. Now what we do in this example, well, we will focus in R1 and we will show its BGP information. Let's imagine that everything is blank, everything is fresh at R1, and the first message that R1 receives is from R3 over eBGP. What's the message? Well, is R3 announces two paths. So what are these paths? Well, R3 is directly attached to this network prefix 10.1, and R4 is directly attached to 10.2. Well, these are private addresses. So it's not very typical to advertise private addresses. In this example, for the sake of simplicity, we are using private addresses. Toward the end of the lecture, we'll see some examples that we still advertise private addresses, but it's not very typical. But for the sake of simplicity, let us assume that we do on this example. One thing that is special about this fundamental example is that R3 and R4 are configured to advertise any prefixes that exist in this domain. R3 is directly attached to 10.1, but it's not directly attached to 10.2. However, it will announce a path to both of these sub prefixes. It is software. We can do anything. We could have modified it to, we could have configured it to not to do so. That's the next example. But in this example, I have configured these routers to advertise any prefixes that exist in the domain ASY. Well, R1 receives these two messages. What would be the ribbon? So let us assume that these two routes are accepted by the import filter at R1. But R1 writes that I have received a route from R3 to this network prefix from this AS, where the next hop is 1112. Well, the next hop is 1112 here, is an IP address if I want to reach the sender of this announcement, which is R3, this interface of R3. And since there is no other route in the ribbon of R1, that becomes automatically the best route. Same thing for the other network prefix. So it receives from R3 route to 10.2 from this ASY. Again, the next hop is 1112. And since there is no other route to that destination, that becomes automatically the best. What about the rebound? Well, R1 has learned two new routes to two network prefixes, so it should announce it to its peers. What is its peer? Well, it should announce it basically internally to R2 over iBGP. So over iBGP, we'll send to R2 that, well, I found these two routes. And the next hop is 1112, 1112. Still, it is here. One of the differences between iBGP over eBGP was the fact that we do not touch the next hop that we observe here. The next hop is still the north interface of R3. That's what I explained here. Interesting case is that, well, in the time that we were discussing about this thing, R2 also has received from R4 some paths, some routes that reaches 10.2 and 10.1. And it will also advertise it over IBGP to R1. So R1 will receive from R2, well, I know a path that reaches 10.1 and 10.2 that comes from this ASY, and the next hop is 2221. What is the next hop? Well, next hop is a sender, external sender of this route, which is R4, is the north interface of R4. Imagine that these two routes these routes pass the import filter at R1, and R1 writes them in the ribbon file, in the ribbon data. Now R1 should make a decision, because per destination, we have two possible acceptable routes. For 10.1, we have a route that the next hop is 1112. For the same destination, we have another route that the destination, the next hop is 2221. Same thing for the other. Now I'm asking you, after the decision process, which of these red routes, the routes that we have obtained from R2, could become the best route? Given what? Given the same sequence that I showed you before, the common sequence. So I'm opening the poll. The first one only means that this route becomes the best instead of this one. Second one only means that this route becomes the best instead of that one, and both, it's both. I will close the poll in a couple of seconds. Closing. Okay. So the majority says the second one only, and it seems that you're hesitating with all of the answers. So ABC, from your point of view, ABC are all possible correct answers, and let me explain to you what is the correct answer. The correct answer is none. Oh. Yeah, it is explained here. Why it is none? Oh, we should look at a set of rules that we have, and we should compare them more. These two attributes are absent. So we go through the next one. Next one is the routes that are shorter in the AS path. They are equal. Well, both of them, the number of AS path that they take is 1. This guy is also absent until we reach this. So this rule is saying that, well, eBGP is preferred over IBGP. So the thing that they have learned externally, the thing that is more fresh, is preferred over something that we have learned internally. But if you look at it, the routes in the gray 1 and 3 are the routes that we have learned through eBGP. So these two routes becomes the best. The other routes, we have learned them from R2, and they will learn from IBGP. So the traffic from R1 goes to this AS always takes this path. Same thing in the R2. Well, the traffic that goes from R2 to this AS always exit the domain as soon as possible. And we will talk about that later. Another fundamental example is also very important, is a similar example. I modified ASX. Well, What's the modification? Well, I added two routers, R21 and R22. Again, the plain lines shows physical connection. For R1, for example, is directly connected to R21. R21 is directly attached to R22. However, R1 is not directly attached to R22. Well, this is the TCP connection that R1 is pairing to R22, right? I'm showing the addresses, the IP addresses that I have allocated here. There is another difference here. Well, this time I have configured R3 and R4 to only announce the network prefix that they are directly attached to. What does that mean? Well, R3 is directly attached to 10.1, and it will only announce this network prefix. It does not announce 10.2 as well. Same thing here. R4 is directly attached to 10.2, so it will only advertise this network prefix. Since it is in software, you're very flexible and you could do both, and people might prefer one over the other. Again, we will focus on R1 and we will look at this BGP information. Let's again assume that everything is fresh at R1. And the first thing that R1 receives is a route from R3. What is the route? Well, this is a route to 10.1. Yeah. Since that's the first thing that R1 receives, let us assume that it passes the import filter of R1. So since it's the only thing, R1 will write it in the ribbon file that I have received this path from R3 to this network prefix for this area Y, and the next hop is what? Next hop is 1112. Next hop is an IP address that I want to reach the external sender of this route. And that becomes automatically the best, because that's the only route that we know to this network prefix. What about the reroute? Well, that's a new route that R3 has learned externally. Well, it will repeat it internally. Well, it will send it to R21 and R22 over IBGP. It's good to remember that the next hop is not yet changeable. It's always 1112. And that's what I have explained here. Again, in the time that we were discussing, R22 has received a route to 10.2 from R4, or it will announce it to R1 over IBGP. For R22 sends to R1, well, I know a path to this network prefix, and the next hop is 22221. Imagine that passes this route, passes the import filter of R1, and it will be written in the ribbon file of R1. Well, I have received from R22 over IBGP a path to this new network prefix, and the next hop is 2221. That becomes, again, automatically the best route. The reroute is also interesting. The reroute is not changed. Why is that? Well, you should think about it. Reroute are the thing that we advertise to our peers, right? So R1, we should see whether R1 has a reason to advertise the new route that he has learned to any of his peers. So first of all, what about R21 and R22? Well, this is something that we have learned internally. By the rule, we do not repeat it internally. So since I've learned this route from R22, which is in the same domain as me, R1 will not advertise this to R22, because R22 will have the first-hand information directly from R22. What about externally? Well, this guy is attached to another router externally. It makes sense to announce this route, not in this case, because that creates a loop. This is a route that you have learned from ASY. You do not repeat it again to ASY because you create a loop. So we have rules to avoid loops, and one of them is this one. A route that you have learned from one AS, you do not repeat it to the same AS. So the reroute does not change, and in fact, R1 does not send any announcement after learning this new route. The interesting case is this one. Again, in the meantime, R21 also receives a route to 10.2 from R3. This time the next hop is different, is 3331 is this interface here, and over IBGP we'll send it to R1. Imagine that passes the import filter, and R1 writes that new route in its ribbon file. What would be? Well, it would be that I received from R21 a new route to Delta2, and the next hop is 3331. Now, R1 should make a decision, because per destination, we have set of 2 acceptable routes. We should pick the best one. And I'm asking you whether this new route will be promoted as the new route, as the best route, given the same common sequence that we have seen before. So I'm opening the poll. No, I will close the poll in a second. Oh, the majority says A, which is the correct answer. So why is that? Well, let me go back to the common rule. We'll see what are the things that we should compare. That's the wrong way. Well, okay. So these are absent. Shortest AS path against that is equal. All of them is 1. What about this one? Well, these 2 routes are both learned over IBGP. So we cannot compare them against each other in this case. And the last one that break the even is this one. We should compute the shortest path to the next hop. And let me come back to the example. Okay. So the next hop in this route is 2221. The next hop in the second route is 3331. As I said, well, the IP address in the boundary are known internally. Therefore, R1 through OSPF knows a path to these 2 guys, and therefore it can compute the cost of this path. So if you compute the cost of this path, well, this route has an advantage is because it goes through 2 links, the cost is 2. The other goes through 3 links, the cost is 3. So the one that is shorter in the has the shortest path to the next hop is the second one. These 2 fundamentals that we have seen here helps us to answer this question, which is an important thing. Here I assume that we have 2 internet service providers, 2 ISPs. Where they have such a network, ISP1 and ISP2 are connected via 2 routers, R12 and R22, and R11 and R21. A customer of ISP1 wants to send some traffic, which this traffic enters ISP1 through R12, and the destination is customer 2, which is a customer of ISP2 at this interface of this router R21. And I'm asking you, this traffic takes which path? Takes the path that R21, R22, R21, or the other way around? Or it depends, or both? So let me open the code. I will close the poll in a couple of seconds. So the majority says C, which means it depends on the configuration, which is a very safe answer. And it's a correct answer, in fact. In the both fundamental examples that we have seen, we've seen both of these cases. In the first fundamental example, we have seen that routers get rid of the traffic, send it to the other domain as soon as possible. This is so-called hot potato routing, meaning that it's like hot potato, you want to get rid of it as soon as possible. And this is what some ISP does. Well, if you receive a traffic that is for another customer of another ISP, sometimes it makes sense to get rid of it as soon as possible. The consequence of such routing, so for example, hot potato routing, is that the traffic that goes from customer 1 to customer 2 take this path, the green path. However, the traffic in the other way takes a different path, which means that the global internet routing might be asymmetric. The routing in different ways, the traffic, the packets in different ways may take different paths. Some service providers might prefer to do cold potato routing, which is the other way around, which means that this traffic goes to R11 and then R22 because you have a customer that pays a lot to you, so you're also an expensive service provider. You want to provide a good quality of service, so you prefer to keep this traffic inside your domain as long as possible, such that you could give higher priority to this traffic, for example. That is called cold potato routing, and both of them are possible and depends on the configuration. For example, in the fundamental example, the difference between the configuration was the fact that if you configure routers to announce every network prefixes that exists in the domain, if you configure your routers to only announce network prefixes that are directly attached. Well, until now, what I've talked about was we had some path, we had some routes, we had some paths, and we passed them around, right? But we should somehow start with the fact that how such routes are originated, what are the source of those routes. And this is what I'm here explaining. Well, you could always do things as static. You could write a config file, and these are the routes on these router nodes. But one thing that most of the time is done, and we will do in the labs, is first one is called redistribute connected. Means that you configure this BGP router to originate all the routes that are this guy is connected directly attached to. So all the network prefixes that this router is directly attached to. The consequence is that you should assume that all routers are BGP routers. And therefore, then you know every network prefix in your network. Another thing is redistribute from IGP. For example, could be which is your internal routing, could be OSPF. Redistribute in general means that you have two routing protocols. You put the information, you put the routing that you have understand from one to the other. That exactly means that it means that you put the information that you have learned from OSPF into BGP, because your router, for example, are running OSPF at the same time. Well, they will learn some internal prefixes, and this would be redistributed to the OSPF, would be to the BGP. One thing that is important, one of the attributes of the route is the origin. Some BGP routers might prefer a route that was learned by BGP rather than something that was learned by OSPF or something that was learned static. We will mark them what was the origin of this route. Well, until now, we talked about routes as they are some distinct objects, right? However, most of the time, routes overlap. That happens very frequently in IPv6. In IPv6, for example, since the space of IPv6 addresses is very large, we expect providers to allocate IPv6 addresses in a very structured way. For example, in Switzerland, all IPv6 addresses in Switzerland can be aggregated as one prefix, right? Then if you have a Swiss provider, this Swiss provider could only advertise that one prefix, because we don't care about the details of the prefixes inside this domain. The rest of the world does not care about it, as long as the packets could reach Switzerland, right? And that makes routing tables much simpler, because you have omitted thousands of possible rows, and also the BGP announcement becomes much smaller because you aggregate things. That rarely happened with IPv4, and I will talk about it later. Well, let's see what aggregation means and how it could help us in a specific example here. Here I'm showing 4 ASs, AS1, 2, 3, and 4. AS1 is attached to a network prefix 2001 BGPBegin. AS2 is connected to another network prefix 2001 BGPF. Well, they will announce these routes to AS3. Imagine they will pass the import filter. They were accepted by the policy of AS3. So AS3 will receive these two new routes where they can potentially be aggregated. And I'm asking you, if these two routes, if these two network prefixes can be aggregated, what would be the aggregated prefix? I've opened the poll. I will close the poll in a couple of seconds. Well, the majority says A, which is the correct answer. When you want to aggregate two prefixes, they should be contiguous. What does that mean? Well, if you look at these two network prefixes, they are exactly equal up to here. Only E and F differ. So if you look at the binary representation of E and F, we will see that only the last bit only differs. So we could aggregate them by /47. So each of them, I mean, we could say BGPB /47 or BGPF /47. That would be the aggregated network prefix. But still, there is a point that is missing here. Yeah, which is the fact that these two are aggregated, but the path is different. The path is go through either AS1 or AS2. So BGP has already thought about that, and this is the syntax that we use in such cases, which is the curly bracket, which means or. Means that to this, if we want to go to this aggregated prefix, there is a path that goes through 3 and 1 or 2. Then, for example, AS4 want to append this path would be 4, 3, 1, or 2, right? So we have simplified things, right? Otherwise, we should have 2 routes. We should announce 2 routes. Now we are announcing only 1. Let's make it a bit more interesting. It's the same example, but for some reason, AS2 also establish a physical connection directly to AS4. Well, you might think that, that this network is not very well structured. That's redundant. In fact, that frequently occurs because AS4 and AS2 have some customers, which is this in this network prefix, and they want to provide a more reliable service to that. So they decide to share a cost of a link and provide such services to them. So AS4 will receive a path to this network prefix from AS2, also receives an aggregated path from AS3. These are overlapping paths. And I'm asking which rows may be selected at AS4 as the best route. So I'm opening the poll. I will close the poll in a couple of seconds. Well, the majority says B, which is good because you think that these two paths are overlapping, so it makes sense to keep only one. However, that's not what happens. In fact, this router in this, I mean, we will keep both of them because from point of view of AS4, these are two different routes. Overlapping routes are considered as different paths, and they are very frequent if you think about it. If you look at the routing table of a router, for example, we have default gateway. Default gateway is an overlapping route with every route. So we treat overlapping route as different routes. So if you look at the ribbon file at the AS4, and if you think that it's only one router, for example, then we will see two lines, one with this one and one with this. Now the next question, well, if AS4 receives some packets where the destination is in this network prefix, which path this traffic will follow? It will go through AS2 directly, or it will go first through AS3 and then AS2. I've opened the poll. I will close the poll in a couple of seconds. So everyone says B, which is the correct answer. And the principle is that we do, as we do in the routers, we do longest prefix match. The row that is the most specific row, the most specified row is the one that we pick. So if we do a longest prefix match, we have a better match here, and therefore we will send it over this path rather than. We will keep the other one. It makes sense because we will keep the other one because that's in the case of reliability. So if this link was broken for some reason, AS4 will detect this loss over the keep alive process, and they will delete this row, delete this row, and the path that the traffic will take now is the above one. So we will keep both, and yeah. So I skipped, and a step here was, so we have a router, which is a BGP router. Still it is a router. It has a forwarding table, routing table, and in fact, that is the thing a router uses to send packets. So we have a routing table where you look for this destination. I should send it over this interface. For a magical step, so what I did was the things that we have in the BGP table was directly used in the forwarding table, but that's not how typically it's done. So there is additional step here, the thing that I'm discussing here. So you have found some information, have figure out some routes throughout BGP. They are in the BGP library. They are, for example, in the ribbon file or in the ribout file. And now we want to put them as something useful, which is we want to put them in the forwarding tables. How do we do that? Well, there are two possible ways to do that. Well, the first one, which makes sense, but is not usually done, is most of the time avoided, is redistribution of BGP into IGP. For redistribution, I said, well, we have two routing protocols. We have learned some routes from one. We will put it in the other one. For example, it's OSPF. So the external routes that you have learned by BGP, you will redistribute them over OSPF. Then OSPF will take care of that. We will pass it around everywhere. Then at the end, every router knows a path to every external destination as well. such thing works with OSPF because OSPF is very sophisticated and can handle large tables, but might not work with other IGP. The other thing that is less natural, but is most of the time done, is called injection. Means that when you have a BGP router and learns a route, external route, it will directly put that route in its forwarding table. It's always done, in fact, in the lab. This is something that is always done. This router does not propagate this route, and this thing will only help this router, and we will see why it is not very natural. But before that, let me give you an example of redistribution. So here we have three domains, three ASS, ASX, ASY, and ASZ. Every router except R1 runs BGP, they speak BGP. And R6 learns a route to 18.1 through a BGP from R4. So this guy learns a route from here, and the next hop would be 222. It will redistribute it over OSPF. Well, 222, remember, 222 is known for everyone inside this AS. So it will redistribute that. Will say that if you want to reach someone in this network prefix, you should send your traffic to this IP address. Now over OSPF, every router knows that, well, if you want to send some packet here, I should send it to this interface, which is exactly as the same that R6 is directly attached. I mean, from other routers' point of view, R6 is directly attached to this network prefix. OSPF is smarter than that. OSPF will mark this route as something that we have learned externally, this type 5, for example. But at the end, what happens is that, well, everyone knows now a path to here. However, in practice, most of the operators avoid redistribution. That's why is that? Because if you think about it, if you're a tier 1 provider that you have a worldwide connectivity, then especially in IPv4, order of prefixes in IPv4 might be 1 million. So you have 1 million IPv4 addresses, and if you want to do the redistribution, means that every router that you have in this domain will flood a table of 1 million thing, and you have a forwarding table that have 1 million rows. These things, OSPF might be able to handle such large tables, large routing tables, but most of the operators decided not to do so. What do? Instead, they do injection only, meaning that a BGP router put directly the route that he has learned externally in his routing table. Let me explain it here. Well, it's the same example as before, but we do not do redistribution here. We do injection here, meaning that, well, when R6 learns this route, it will put it in its forwarding table. Also, R2 will learn this route through IBGP. They would put it in their forwarding table. And I'm asking what would be the next hop in the forwarding table at R6 as R2. I will open the poll. So for R6, it's easy, right? For R6, the next hop is 2222, which is R6 is an unlinked interface of R6. The question is really about R2, whether the next hop is here or is still the 222. I'll close the poll in a couple of seconds. The majority says B, which is exactly what makes sense. But as I told you, it's a bit, this injection is a bit unnatural. In fact, what happens is that Well, R2 puts exactly directly what has learned through BGP. So what R2 learns through BGP is that, well, there is a path that goes here, and the next hop is 222. It will put it exactly as is in its forwarding table. Therefore, the next hop would be 222. But that creates a problem, right? Because whenever R2 wants to send some packet to this destination, if you look at its forwarding table, the interface is missing because this IP address is not on link. It is shown here. For example, it's another example. Well, R1 has learned a route to this guy through BGP, and the next hop is 222.63, as I told you. It will put it exactly as is in its forwarding table. The interface is missing. But if you look up the table, routing table at R1, you cannot decide what to do with this packet. That is solved by recursive table lookup, meaning that if you look up the forwarding table, the routing table, you could not find the interface, look up again for the next hop. What happens here? Well, this R1 will look up the forwarding table. You see the interface is missing. It will look up again for the next hop. Hopefully, there is another row obtained through OSPF, for example, saying that if you want to send to this guy, you should send to this interface here, to this IP address here at this interface. Well, I should stop here. And the professor will take over of the lecture next week. So thank you very much.